Okay, it's like the same. I will ask Dan you to be a host and then change me as a co-host.
Okay, no problem.
At a moment. Okay.
ช่วงนี้น้ำท่วมฝนตกคนจมน้ำคนจมน้ำตาย
Okay, Dan, so you are host now.
Thank you. Let me
Yeah.
see. Yep. Hello, good afternoon. Can you hear me? Is it okay?
Yes,
Yep, good.
perfect.
One moment. Let me get everyone in. Hi, sorry, I had a little bit of accident last night and I had to stay over like ER for the night. Yeah, one moment. Oops, this one here. So I had to cancel the morning session. So we will just move the 2 lecture session to this one and the one afterwards and reduce the tutorial. I think everyone is don't really have problem with the code anymore. So it's very straightforward. So maybe we'll just move right straightforward with the contents. Just a general question. So I assume everyone has played a little bit with the LSTM models last night. How is the performance? Did you guys get like significant better score than the neural nets, or it's like very similar? Okay, we add as a co-host. One moment. So maybe let's go through the models of the LSTM models. So what is the best score? So maybe we'll start with someone to as a start of conversation. Thomas, hi Thomas, are you there? Since you're right below me. Hello? Okay, maybe he's not there. So let me see. Virginia, so have you shared your models from yesterday? Can you share your model from yesterday?
I didn't share my model. I didn't save too many models from the LSTM because it took a really long time to run. And I was honestly a little bit busy with some other meetings as well.
No worry.
But the ones that I did run, just in case you are curious, were not that much better. They were a little bit better, but still around like, I think yesterday, some of the lowest numbers we got were like 0.6 or 0.006. Mine was still like 0.09 or 0.009. So they're not as good as some of the ones that we saw yesterday. Maybe a little bit better than my results on the first model. But that's also just because I think I started to get a better understanding of how to control the decreasing and increasing of the dimensions and the dropouts and things like that. So maybe it's partially I'm learning and the neural net.
Yes, like we're learning at the same time, making it better. I'm just curious. So, Boshen, do you have a sample like LSTM model structure that you can share?
Yeah.
What?
I did several of them and I only saved 3.
Yeah.
So this is the best one I got. I'm sure someone else probably have a little bit better performance than I did, but I stick to 20 epochs. A major thing that I changed was the initial starting points. Instead 16 units, I changed it to 64. I think oh yes. So there was I discovered that if so this is the 64 units one performed a little bit better than the units I changed it to 128. I think the major reason is because the batch number. So the one that I did, which is the starting unit is 128. The batch number was 32. So I thought that was pretty interesting. Um, uh, you can kind of see the radiant descent as slightly different, but the sample predictions is about the same. So that's what I discovered.
Yeah. So I think it's very interesting. So for example, remember in this case, it has like if you look at the amount of total parameters, it is like a far larger number of total parameters than the comparing to our traditional neural net, because LSTM is like very parameter heavy. So that the problem with those like big, the large amount of parameters, that first of all, it needs a lot of data sets, and second one, it needs a lot of epochs. So if you have noticed, like in the earlier neural net models, maybe after like 5 iterations, it start to reach a plateau of for the accuracy. It's like when you start to increase the epoch. I'm not sure. So this is
Yeah. So this
so
is the
this is
new one. This is the earlier one.
Yeah, so this is for example, like this one. So it sort of start to get flatline at the end. For example, like it became overfitting. Overfitting is that in the end, you're seeing like more features is captured for our training set, and the less features is captured with our validation set. And it start to sort of flatline at the end. It means if you have trained it for more iterations, it's may not be able to catch like any more characters, so the accuracy would like flatline. However, if you're looking at like a LSTM model, you see this model is far more like capable of describing like the core relationship. And also because you only train like a 20 epoch, you can see the trend here. If you train it for another 20 epoch or like 50 epoch, it's likely that your like the accuracy is still going to increase. So it did not reach like this kind of plateau of accuracy, and maybe with a bit of like learning rate decay, you can easily sort of break your current value loss of like 0.003 and capture more information. So the thing about the different neural network structure is that even though in theory, like the more iteration you train, the more accuracy the more accurate it become. But like a different neural network structure have like a different capacity of capturing. So they have like each one has like a different limitation on the maximum accuracy it can achieve before it become overwhelmed with like minor details.
Right.
So this is
Yeah, I also try. So the one that I saved, I think all of them is Relu. I also tried to use Sigmor yesterday.
Yeah.
Um, it didn't perform very well at all. So basically, I stopped halfway through the training. But basically, it started probably at 0.06, 0.05 at very high, and then the performance didn't. Uh, uh, didn't result a good outcome. So I kind of stopped it. Yeah.
So that's when you're using the sigmoid function, right?
Yeah, that's when I use a sigmoid. Yeah, yeah. And I tried a couple of times. It's still came up with similar outcome halfway through. So because the training process takes so long, and that's when I stopped.
No worries. So I think that's the main problem with sigmoid. So I think we have talked a little bit about it, like the sigmoid, because let me just quickly sketch. Annotate. Yeah, I'll just draw here. So if you remember, sigmoid function is something like this. Sorry, wrong one. It's not sigmoid. Sigmoid function is something like this. So this is 1, 0, and it's something like this. So basically, like a large amount of like and xy will contribute. A large amount of x, like in those regions, will very like contribute to like either 0 or either 1 as an output. So sigmoid is very good for classification, like the 0, 1 question, but it's less effective if you're doing regression, means we actually want a value instead of just a label says like cats or not cats, dog or not dog, like tree or not tree. So that I think this is the reason that the sigmoid function doesn't really work or work a lot less in this scenario comparing to ReLU. ReLU is something like this. So yeah. So ReLU is something like this. So for example, like all the x here, you will get like different y, versus here, like all the x here, you will get like a very similar y. Yeah. So so I think this is a reason why I think like a sigmoid works less in this scenario. I'm wondering, have anyone tried like something just maybe with 1 LSTM layer and 1 dense layer, like a very shallow net? Not necessarily shallow, but like with less layers. Has anyone here tried some neural net with like only 2 layers or 1 layers, just 1 LSTM layers? Oh, weird silence. Yeah. Very quiet. So no worries. So are there any like living people in this group that actually did like another LSTM training? Lot of silence.
May I show my screen?
Yes. Thank you. Yeah, it's very weird in Zoom meetings. That's we're not really sure if people are there. Yeah.
Okay, so the result I got is slightly better than yesterday, but not much better. I tried a lot of different parameters. I first started with SGD, but then I had problems with the learning rate. It's either too slow or then I changed learning rate. It became too large and it didn't decrease. Instead of it decreases first and then it started to increase the loss. So I think it might be a problem with the learning rate. Not so sure. And then I checked the Keras introduction, and then I changed the optimizer to RMS prop, and then that's the result, the best result I've got.
I think it's great. So I think RMS prop, I forgot if it has a decay quality, but I don't think it has a decay quality, but it was like a bit more effective comparing to the Adam, and it's like a lot easier to maneuver compared to SDJ, which has far more parameters. And but I think this is a good choice. And the one thing I noticed, like compared for yours, is that like you're having 1 LSTM layers and the 3 dense layers, and in this way you're able to achieve like, I think it's slightly better results than our optimized result from yesterday, because I remember our optimized result from yesterday is something like 0.06 or 0.059. Just wondering who has the best results from yesterday? So that's the model score of 0.0059. Whose model was that? I'm wondering if we can pull up that. Is that also yours?
Yep.
Oh, perfect.
Show that as well.
Yep.
Um,
Yeah, so it's interesting.
Um,
Probably like
yes.
everyone has this feeling about neural nets. So it's sometimes the structures and the parameters, you sort of have this very intuitive explanation on what works and what's not. But a lot of them are just really depending on like experiments and the previous experience to like to find out what are the best combinations. And maybe like a change in a small parameter such as an activation function or like a layer structure can lead to significant increase. So I think like this one and the one you're having today are very similar structure. Can we take a look at
Yeah,
what?
that's the one I got today. And then this is yesterday's results.
So I think so it's the 2562. So basically I think you have swapped the first two layers with the LSTM layer.
Yep. And then I also
Re-
I reduced the dense layer because then it got too slow.
Yes. So by this comparison, you can sort of see that the LSTM layer is far more efficient in describing the features and the connections in these datasets than comparing to the dense layer. For example, just ignore the flattened layer. It doesn't have any parameter to train, but you can see in the SLTM layers, you have like a one with 128 neurons, and this one replaced the like can you show the dense structure? So if you take like a comparison from that, so it basically replaced the two layers of like 56 neurons and one 28 neurons, and it also decreased, I think, the neurons in the layer 3 and the layer 4 in half. So we basically have replaced a lot of the neurons in the previous structure with one SLTM LSTM layer, and we achieved like a slightly better score. But because like it's already quite accurate, so like even a small increase is like a big step. So I think, but comparing, so that one was like 0.059, this one is like 0.053. So it's already like 10% increase in accuracy. So just by comparing these two model structures, we can sort of see the LSTM layers is far more effective. Yes, we know it's very slow to train, but it's possible to achieve like a higher accuracy with this one. Because it like, for example, if we continue to train the neural net model and tweak the parameters, it's a bit unlikely for us to achieve like better than that score, a score better than the one she's showing. But for the LSTM layers, I think there are a few parameters we can also tweak to in search for a like better outcome. And also one significant element for us to evaluate if this model structure is really working by which structure is working better is this space. So is this gap here. So this smaller of this gap, it means that this model is capture the general features like in the data sets. And however, if you look at the neural net model, can you move to the neural net? Yeah. So you can see like very far up, and it's the same with, I think it's the same with all the other neural network you guys have been trying yesterday. Like this, there has always been a very significant gap between them. Means it start to get overwhelmed in the explicit like minor details that may be only applying to the training set, while it's less efficient in capturing details, like the general details that applies to everyone. So like checking out like if there's a large gap between your validation set and the training set, it would be like a good way to evaluate if the like model has a strong like generalization ability, means it has a strong ability to capture the essence of the relationship in the data sets. So basically the one with smaller gap has more potential of optimization. Okay, so does anyone has like a even better outcome compared to this one, like a better score? So this one will have like 0.0053. Anyone has like a better outcome? So let's assume that's our like best score of this course. So thank you. Sorry, how to pronounce your name? Shelly. Xiao. Okay. So thank you, Xiao, for providing our best model of this course.
Thanks, Dan.
Welcome. Also, can we have a look at the like a visualization of like what's the outcome of the like overlapping of the two curves, like your prediction versus the ground truth sample?
You mean the bottom diagrams? Yeah, sure.
Yes. Yes, so we can see with this model, like it's already has like extremely high level of accuracy that we're able to work with. So it's unlikely like this kind of model will have 100% or 0% loss or error, but it's just depending on the scope of work and what kind of error range we can accept to see if the model has met our expectations. Of course, there are a lot of like computer scientists who are overwhelmed with the like accuracy of the model, and they would like change a lot of structures and a lot of parameters to get to increase its accuracy for like 1%. But for our case, I don't think it's necessary. It's just that when we start to answer the question, we need like a very clear goal of like what kind of accuracy is acceptable for us to be applied in reality, because I think architecture and even the civil engineering has a lot higher tolerance for errors comparing to other industries. So it's really depending on the framing of the problem and the accuracy that we're looking for. So it's not necessarily that we have to try everything that's in to find the best models, but as long as we have the one that works for us, it would be great. Yeah. So thank you.
Thanks.
So I'll quickly show my screen here. One moment. So, everyone see my screen? So in our last session, we'll talk a little bit about like machine vision and smart material processing. So this one is based on like one of our recently published paper, like recently as published like a month ago. That's this is one of the projects that really have significant commercial application and actually sponsored by our industry partners. Because in the previous 2 days, we have shown like the more ideal exploration research projects that are exploring some ideas in the boundaries. But now we're trying to address like what kind of what's the essence of this technology that can be applied to our modern industry that we have like we can have direct benefit from. So this one is a industry sponsored research that has like significant industry impact. So this one is a perhaps let's say less exploratory but a lot more practical comparing to the previous models. So this is a project is actually based on a real challenge that timber industry currently face. So in the timber mills, parallel to the production of structural graded timber, owing to the unpredictable quality of natural materials, the factory will generate a lot of like this kind of undergraded timber. So basically we have a lot of like timbers like this has defects in it. So it generally it fails structural grade tests. It cannot use as like a timber beam, timber trusses in the industrial settings. And a lot of them, as they're undergraded, they were just sold at a like far cheaper price. And this is so like a common strategy to recover those, let's say not unusable, let's say just the undergrade timbers, is to marking and removing of the defect with generated medium lengths of the like clear wood, like the structure positive piece of timbers, and then join them together into a single full length structure timbers. Normally they're jointed with this kind of timber joint that are very structural. And in the industry, the process goes like this. So one moment. So basically there is a workflow that, so this one, each of these strips is actually scaled down to in the X direction to one fourth of the original length. So it's basically sort of shrink down on the X direction to fitting onto the paper. Otherwise, it's one of these very slim and linear timber panel that are generally like 4.8 meters long. So basically, each of these timber piece, like timber beam, will pop through the millings, and there will be like a worker, like a human there with a marker, look at them and say, okay, there's a defect and here's a defect. He will use a marker to mark out where the defects is, and then he will mill out of the defect. It's like the third step to generate all those like smaller segments, and these smaller segments will then feed into a finger jointing process to join them together into this kind of like full length timbers. So this is like how people like in the timber industry use this method to cut away the defects and join together like let's say the good parts, the structure graded parts, and into a full length. And in this case, we were trying to see if we can use AI and machine vision to optimize this process to reduce the waste of material and generate a more like effective system, because currently it's all based on like what the workers see, and a lot of the experience is not transferable among them, and a lot of time they would just mark out like a larger area to avoid the nuance at the boundaries. So in this case, there were like two elements we're exploring them. One is that if we can use AI and machine learning to better recognize one, and the second one is that we're trying to see if we could develop an algorithm that could join them in a more effective manner. That is like, because if we're joining the piece, for example, like the target length is 4.8 meters, but if we join it to a piece to like 5 meters, we have to chop off at the end and to make them like end up with a uniform length. It's like required by the industry standard. So we're trying to see if we can optimize the jointing process to have less chopping out at the end, like less waste of materials. So the first challenge is the defect detection in the timber processing. And because currently we're working with those images that are provided by the timber mill, so basically the timber mill has a process called MO, like the structure test, I forgot, like the MOE, like module of elasticity test, because basically for each timber piece to go through this machine, and the machine will scan the surface image of the timber and generate MOE data based on the like strengths at each individual point. And we're trying to utilize the image that are just directly output of this scanning process and use this one to create our preliminary simulations of investigation. So there are like 4 steps. So first one is image denoising, and the second one is just undistort the image and removing the background. The third one is we need to calculate the probability map for the distribution of the defects. So like where is like higher probability for the defects. And the step 4, like we're cutting the image in simulation, but in reality, we should be cutting out the timbers according to the probabilities of defect. And here, so those in this system, those like are how we're achieving this function. So it's like very small project to show in like capacity of the algorithm and AI. So for our project, we have to start with a little bit of cleaning up of the image itself. So we can see here, the top part is the image that just pop out of the scanning mill. And there are a lot of like noise on the end that can somehow be disruptive to our algorithm of visualization and prediction. So the first time, in the first phase, we're trying to get rid of all the noise at the end. And we use like a very similar method of regional detection to measure like the width of each non-black pixels. If the non-black regions, if the region has like very short width, it means it's likely to be a spike that in this case, we're going to fill the pixels. If the non-black region is say it's very long, it means it's part of like real timber, not the noise on the edge. So we use like a very similar region detection method, like comparing to the 2D processing, to get rid of the noise on the edge of all those scanned image. The next step is to undistort the image. So this is not really important to the, let's say, calculation of the probability maps, but this is just important for the visualization process. So because like going through the scanning mills, the timber is likely to be like shifting a little bit along the y-axis, x-axis, like shifting a little bit because of the vibration of the machine. And also some of the timber are just slightly bented. It's likely that a lot of the image outcome will looks like this. So it will have like this weird bent upward. So in this case, we're just basically, we start from the bottom and start to look upwards. And let me get this one. If we can, oops, share. So basically, we'll start at the bottom and look up upwards and find those regions of like non-black pixels, and just pull this pixel to the bottom. So we just pull each strip to just right to the bottom, and afterwards we'll just chop out the top part of the black pixels. In the end, we will have like a very clean, aligned like timber scan like this. So it's always start with a little bit of image processing, so you have like a cleaner data sets, which will decrease a lot of problem. And the step 3 is a calculation of a probability map. So this one is quite interesting. So there are 2 ways of doing this. So there are like the traditional way I'm just showing here. So when you're fitting them into a machine learning system, the one thing is that they can come from this like image segmentation map. So this is like more image segmentation. So it will have give you an yes, no result on where each area is. So the red area labeled here are like the defect areas, and the green area here are labeled as good timbers, and the purple are just background because we're just trained with those data sets. The training process is crucial. So basically we have the workers marking out where the real defects is, and we use this as our ground truth data set. So basically, like ideally a human or a worker would label out the image B. So this one, so this is ideally we start with like human labeling image A and color coded into image B. So in this one, we have a ground truth of like what each pixel stands for. For example, this pixel is a background pixel, and it basically it will have let me get something. Maybe I'll share screen here. So basically for this one is that we're having so this is an image, and so those are the like defects. And for each of the pixels on the image, it is giving a label. So this label looks like it will have 3 numbers. So it's probably, for example, it's a good timber. So it's the first one is non-defect timber. So it's probably called like 1, 0, 0. So this label is assigned to this pixel here, means it is good timber. This is a probability of being a good timber, and this is a probability of being bad timber. This is a like a label, not probability, but a label of being background. So you can imagine in the original image, it has 3 layers of RGB. And then it will also match it to like, it's sort of like 3 layers. I'm just using this one as like, so it's easier for everyone to understand. We'll end up with each pixel of RGB will match to 3 layers of, let's say, good timber. Oops. Or bad timber or defect, or a value describing if it's background. So the dimension of the input and output is like exactly the same, but you start with like RGB value of like, let's say 192, 180, just hypothetically like 72, to this one like 1, 0, 0. So this is like the mapping process that we're used to describe this data set. So it is clear. Ideally, it's not that hard to understand. Yeah. Let me know if you guys encounter any questions or there are any aspects that I didn't like explain clearly. So come back to here. Let me stop this one, stop here. Yeah, because I think it's crucial, like whenever we're looking at this kind of machine learning task, it's crucial for us to identify what would be the data structure of the input and output to achieve this one. And remember, we started with an LBG image and we end up with 3 layers. So the C, D, E are the 3 layers. So the D is a probability map that we generated for the non-defect timbers. So for the non-defect timbers, remember it in the output, in the label, it's only there to 1, but we have the option of generating a probability map of how many during the training process. So how many percentage of let's say likelihood or probability that this one is going to be timber. So for if we're looking at the layer C, so this is a layer C, that we can say the white region, which means 100%, where like the whitest area, it means 100% that we are confident this is a non-defect timber, that's a good timber. And while the black areas that we're sure that it's not a good timber, we don't know if it's like a defect or it's a background, but anyway, it's just not defect, it's just not good timber. And if we look at the image D, we'll see like it shows a probability map of the defected timber. So basically the white area shows like the highest likelihood of where the defects are located, while the black backgrounds in the black areas shows the likelihood of the being not a defect. So the black areas could be good timbers, the black areas could be background, but generally speaking, they're just not timber defects like knots and etc. And the image E is just like a side product. It's used to predict where is the highest probability of the background. So if we didn't use the previous processing method, we can use this one mask to remove the background. So this is a core area of classifier that we have prepared. But in this case, because we didn't get too many of this labeled data from the workers, so we didn't have enough data to actually train a proper neural net. So we used a classical method called the random forest tree segmentation to train this neural net for the image segregation and the image detection. Actually, this quality is achieved with just 2 labeled image from the factory workers. So if you become very fluent with machine learning and other algorithm, it's possible to train a model that's based on very small data sets, just based on 1 or 2 labeled image instead of 10,000 labeled data. But there are a lot of constraints on this transfer learning or this kind of more classical machine learning process, or you can use transfer learning in neural nets to achieve this one. But it just requires a little bit high level maneuvering of the system. And the second part is that now we have learned where the defect is. The second one is the challenge is on timber combination. So basically where to cut the timber and how are we joining them together. So hypothetically, we're having the area with a higher probability of the defects cut out, and there are a lot nuance of parameters from industry settings on that controls this process. Let's say what's the smallest defect that we can cut out, and what is the smallest good timbers we can keep. So there are some nuance in the parameters. But the combination is another challenge on its own. So imagine if you are in a timber mill, the problem is that the timber will come in 1 by 1. So it's very unlikely that you're going to cut 100 pieces of timbers and end up with 1,000 pieces of fragments, and you are trying to sort through them and try to join the piece 1 to piece 298 and to piece 560. In fact, the timber would come 1 by 1, and you cut the first timber, have let's say 5 segments, and another 5 segments come in. We have to make decision on flight that if we're going to use the new upcoming timbers to join it to our existing pile, or we're going to put them into like temporary stack piles of unused timbers that in case we need them, we can just get the new one from them. So there are a few, let's say the few challenges here. So the first one is that we have to join them into a user target length of 4,100 millimeters. And of all combinations, those with the closest proximity to the target length are prioritized for the join. So we want to have like as many accurate 4,800 length jointed pieces possible. We want to avoid those of like 2,900 or 5,000 jointed lengths. We want to avoid them because we don't want to chop off at the end. In that case, we're going to have waste in the material. And on the receiving the new input segments, the new segments will join the leftover segments in the dynamic stockpiles while waiting to be joined. And the dynamic stockpiles are rescanned and updated to find the possible best combinations and the join priorities that meets the previous two criteria. And we also monitor the amount of wastage that come from the difference between our target length and the actually joint length, which may need to be chopped off. And in this case, because so this is like a programming logic. So this is not actually machine learning, but there are also a certain level of intelligence in this. So like, how do we join them? There are two methods of searching through the stockpiles. And the one is what they call the exhaustive recursion. So for exhaustive recursion is that you find all possible combinations, and from the all possible combinations, you're trying to evaluate which one is the best one. But if you're ever good, anyone who's good at mathematics, you would see like probably a stockpile of 20 pieces. We would have a combination of 2 to the 20th power different combinations, and with a stockpile of only 20 pieces, you're going to crash your computer. Your computer will never make the decision fast enough in industrial settings, because it's impossible for everyone to wait like 10 minutes for you to make a decision on what to join or not. So in the end, we use another logic called backtracking logic. So it's another search algorithm. So I'm not going into the details. So basically, this is the algorithm that you start from the bottom up, from the last piece back to the first piece, that would significantly reduce the amount of searching iterations and the amount of the computational power for the calculation of the best combinations. So this is the result of this algorithm. So this is after popping in the first 10, let's say, undergrade timber after cutting in a joint. And after because this is on-flight processing, so it's basically you pop in the first timber, it will make decision, and then you pop the second timber, it will make another decision on what to join. So this is the end result after you pop in the 10th timber. This is what we got. So those are in the dynamic stockpile. So on the dynamic stockpiles are the timbers that we didn't use. So because those add together, it didn't meet 4,800, didn't meet our target length. And on the right are the jointed timbers. You can see the segment length is here, and this is the joint length on the end. So you can see out of those 1, 2, 3, 4, 5, 6, 7. Out of these final 7 boards, actually 6 of them has meet our expectation. That is 4,800 meters, full length, has meet our expectation of full length exact. So there is absolutely no leftovers. And there is only one timber that unfortunately has a little bit of a leftover. But in this case, as you may see, this system of finding what to connect, what not to connect on the fly is extremely efficient. And here are some statistic on the efficiency of the system. So you can, especially on the A, it's the accumulated segment length. So those are the unused segments, so we only have a very limited in the stockpile, so it doesn't increase over time like the waste. So while like in the B and C, we can see the number of the timber pieces inputted and the number of the completed piece like outputted. And here is just like smaller simulation that we have delivered for our client to see how the system works. So the first one, so this is not like so this is our like calculation on the flight. So on the gate next timber, it will go through this segmentation process in the background. And on the middle part we're showing like the segments in the stockpile. On the right part, we're showing like completed joint timbers. So you can see each time we get like new timbers, our segment stockpile changes and our completed joint timber stockpile changes, and how like we're having more and more completed pieces. And on the background, we can track on the wastage and the efficiency of the system. And in the classifier, we also trained like different models that have different performance, so that like our client can switch through them or make a comparison on which one works better for different like timber species. And based on this, we also raised another question, because before that we're trying to mimic the like manual process of having a human marking out where the defects are. But in fact, there are a lot of potential for more controlled method of evaluating where the defects are, because the way for human to evaluate is based on our visual cue, and it's very let's say somewhat intuitive and very experience based, and it's very difficult to increase the accuracy because it's really based on the experience of the worker. But so this is the process of the MOE, like mechanical grade testing system. So with this system, we're not only able to get this scan, but they're all able to get the MOE data. Let's just see, like it's a white curve, which are the strengths. So remember, like the 0 is on top. So obviously in this case, we can see there is a small defects in the middle that significantly damage the MOE value. So here are the weakness point. So in this case, we're trying to redevelop this system and trying to match the timber grain just directly to the structural strength at the value, instead of just classification of good or bad. So, and so we're still working on it. So here are some preliminary models that we have developed. So the white curve is our ground truth, and the pink curve are our predictions, because we only had like 200 timbers in these data sets, and there is no way to transfer an existing model unlike classification. So I think like we're a bit constrained on the size of the data set, but we're asking our sponsor for more information on this. And there is some very interesting aspects in this process. So in this process, now we just go back to the mechanical process first. So we will say like the MOE. So the MOE value refers to the strength of the timber. So the strength of the timber is actually calculated in this way. So a timber piece is fixed on the two end, and there's a loading cell in the middle that trying to push down on the timber. And it will evaluate how much it pushes down and convert it to a like module of elasticity, like strength value. So in the end, like let's say the value at this point is due to the performance of the timber between the two span. So it's not only like a point value, but it's actually relates to the, let's see, let me sketch something here. So for example, like the value here, it's actually it's actually related to the timber quality in this entire strength, entire length. in this entire area. So I'm wondering if this is obvious. So basically you're pushing down on this entire segment of timber. So it's not a point strength, even though it's evaluate or calculate as a point strength, but this number on this point is actually related to this entire segments. And in this case, we have noticed that if we're trying to predict the value of these segments, we need to input like the image from like this entire region, because this is just how the system works. And if we're trying to evaluate at like a smaller region, for example, if we're only going to input some image in the image in these segments and trying to predict like the value on the value here, yeah, like the value in this section, with only, let's say, the image from here, it will result in a very high error rate. It's just because of how the data is collected. So for the machine learning, if you're doing with the material, it's very crucial just to take another look back to how the data is collected and what is the mechanical or the physics just behind the system. So even though it's more like a witchcraft, but it does relate to what's happening in reality. And in this case, if you have noticed that there will be a slight disjoint between, let's say, for example, here is where the defect is, but you can see here is where like when you calculate MOE, like this section is where like has the lowest score. It's not because this point is the weakest, it's also because because this region in average is the weakest. So there is like a disassociation between like the weakest area and actually where the defect is. And also another problem due to this system is that on the very end, so you can see like the white is our ground truth, and there is an area that's just simply missing on the end. And this is a reason because of how this data is collected. You need something to fix here, and apply force here to get a value at this point. And because it's not long enough, so like because we can't fix the timber here, so that we can't have the value in this like two end region, which is quite long. So I think each is like 60 centimeters long. So there is a void on the two end. So another challenge is that if we can calculate what happens to the strength at the two end, for example, here, even though this timber looks very good on all those areas, but because like we're having a big crack here, so perhaps it's still like below grade because of having a big crack at the end. So we're also trying to build a model to predict like the performance on the end without having being able to input like for the entire length of 1.2 meters to make the prediction. And we do have some method that is, maybe we start with infill here. So we start to make a prediction on what's happening here based on the image here. So we start to make a prediction. And then with this prediction, we feed into the same neural network to generate the data for this point. But obviously, like the accuracy on the edge areas will be, well, let's say will decrease. There'll be less of the accuracy in here comparing to the lower of the accuracy in here comparing to all the middle part. So this is, but it's better than nothing. And there are some other ways. So maybe we're thinking of having like a two-layer of system. So currently we're having like the entire 1200 millimeters fit into one like convolutional neural network and have a like accumulate MUOE. And another way is to fit like smaller segment to their individual neural network and have a like a local MOE, and with this kind of mathematic and finite element system, we can have the accumulate MOE. So in the end, the gradient descent will just respond on those kind of like smaller segments and we could end up have like smaller neural network that work with like smaller segments of the timber instead of like a full 1200 lens. I'm showing this project is because this is very different from the previous ones. So the previous ones we're only working with linear materials, and this one we're actually working with like 2D materials and the 2D inputs. Also, this does build like a foundation for other research. For example, how to match like 2D surface pattern to like material property, or match 2D surface pattern to 3D deformation. In this case, like the data is a result of the 3D deformation, but it's only like one axis. But if you're able to have, let's say, the a 3D scanner or live positioning trackers, that we can easily map like this kind of 2D patterns to like 3D deformations. So it's like definitely within the possibility and the ability of the neural nets. So I think this is like a very good introduction project to explore if the same system can be expanded to 3D, 2D and 3D materials. And it's also a good demonstration on how this system and can be used in a more industrial settings and really bring some profits from the clients. So before we move on to the more technical part, I'm wondering, like, are there any questions or ideas about like neural nets in general, or like about these projects, or what's on your mind? Anyone want some start a discussion? Very quiet. Sorry.
I guess I have a question. So the neural network training is not at the parts that to find out where it needs to cut, where the good part is. That's in the image processing part. And the neural network part is at predicting the MOE, or there is multiple neural network do different things.
So there are like 2 projects going on at once, and our goal is always just by reading from the surface data or the scan or a picture of the timber to identify where the weaker part is, like the defect is. But the only question is that how do we label where the defects is? So there are 2 neural network we use. The first one is like a classification. So like if you know, like binary classification, yes, it is a defect, it's not a defect, and etc. So this one, and the difference is that in this case, the data is labeled by the human. So the human would come here with a chalk and say, okay, here, I look at this image, here is a defect. The second part, in the second experiment, the difference is that it's a data, like for example, labeling where is the weaker part is actually collected from a testing machine. So the testing machine will label out where the defect is, and then it's not only going to give you a 0 and 1 answer, say yes, a defect, no, not defect. It's actually going to give you a value of strength on that area. So this is like the main difference in the 2 iterations.
Okay. So that process is not a streamlined process at the manufacture part. Is that correct?
Actually, let's say the data collection, like the part of so the interesting part is about MOE data collection. So this is actually part of the manufacture process. So they do like evaluate if it passes the structure grid test or not. But the problem is that because that's like a machine from another company, so it's not open sourced. Even though they can have the data of like where the weakness part is, where the stronger part is, there's no way for them to take out the data live and connect it to their fabrication machine. So in this case, it became more powerful for us to use image recognition is because they can actually just put a camera on top of their like the pipeline, and the camera can just have like information feed into the fabrication process to make a decision on where to cut. Because currently it's just a human with a marker doing the same. But if you get like a camera and not even a robotic arm, but easily like 3-axis like drawing pens, you can do the same with a more automatic process. So,
thank you.
So I think this is also one powerful part about machine vision in industrial settings. Is that it doesn't require some very expensive novel machine. A lot of the possibilities can be achieved just by adding a camera. Now, probably you need a good camera, but it's a lot cheaper than those kind of professional machines.
Right, and you mentioned the mark timber. You only got 2 samples of it, so you use the image classifications to multiply the samples that you have, right? By reducing this, by basically cutting this timber into smaller segments.
No, actually, there are another ideas called let's say transfer learning that maybe I'll just cover it a little bit in the next phase. Called transfer learning that you can use a pre-trained network, transfer a pre-trained network for a different purpose with very small data sets. For example, we already have a neural network that are trained to recognize cats. And now we want to readapt it to recognizing dogs. So we don't need to, for example, we have the cat neural network trained with 10,000 images of cats, but now we want to adapt it to dogs. Maybe we only need like 50 images of dogs to transfer that neural net to recognize dogs. So this is called transfer learning, but of course, like there have to be some similarities in the original neural network and your end task. But because image classification is an extremely common used tool, so there are a lot of like pre-trained classifier that you can transfer it to your own purpose without using like a whole bunch of the data set.
Got it. Thank you.
Welcome. So shall we get like a 10-minute coffee break and come back at, let's say, so this is 12 20, like a 25 past 3, but not 25, like 15, like 20 past 3, we come back and to look at the more technical version of things. Great, see you. Hello. Is everyone back? Yeah. Great. So for those who are back, do you guys mind just open your camera so we can take like more like a group photos? Sorry, this is like the only way to take group photos nowadays. Yeah. Anyone else? Hello. Uh, so whoever sees this message, so please just turn on your camera. Let's take a group photos before end of the day. Okay. Anyone else coming up? It's okay, and maybe we'll Photoshop other people's sound on it later. One moment. Here's my print screen. Sorry, one moment. How do you guys usually print the screen? Yeah, this one. Perfect. Everyone has a nice big smile. All right. Thank you everyone for still staying up so late or early. Let's move on to our last, the model of this workshop. Just 1 second. Let me share my screen. So the last model structure we're talking about is called CNN. It's a convolutional neural network. Probably a lot of you have heard about it. So this neural network is mainly used for image processing. Obviously, it's also used for like speech recognition and a lot of other tasks. But this one was initially developed because it's a strong capacity to process image. And the typical of the CNN network, so it's like the sequence model that recurrent network. It's characterized with one of these recurrent layers, and for convolutional network, it's characterized by having one of the convolutional layers. And there are two common type of convolution layers, and one is this one. So this one is just typical what we call convolutional layers. And how these layers work. Let me see. Is that, let me see if we can sketch here. Yep. For example, this is your input. So as we said, it mainly works with image, or it started developed to work with image. So this case we use this is called a 3x3 convolutional layers, and this is the input image. Imagine all those numbers like 7, 3, 2, like 2, 9, 4, 1, 2, 8 are like say the RGB values of the image. And it will be fed through a kernel. So kernels are essentially a pack of zeros and ones. And then they will, like, for example, 7 will multiplied by 1, like 2 will multiplied by 0, 1, I don't know if you guys might see my mouse. I'll just use this one. So for example, 7 will be multiplied by 1, 2 will be multiplied by 0, 1 will multiply by 0, like 2, get another color. 7 will multiply by 1, 3 will multiply by 1, 9 will be multiplied by 1, and so this will be likely 0 because it's multiplied by 0, and they're all mathematically very simple. So 8 will be multiplied by 1, 4 will be multiplied by 0, and 2 will also multiply by 0. And if we do this process, we'll have like a 7, 9, 8, because those were only the values that are multiplied by 1, and those adding together will equals like 24. So basically you multiply this pack of numbers with the kernel and add all the results together. The question is that why is this network very powerful? What is this powerful for? Remember, like this is like 1 1 1 0 0 0 0 0 0. This one can be trained, which means this kernel can be like 1 1 1 1 and with 0 0 0 here. I'll just quickly sketch out something. Oh dear. Let's see here. Oops. So for example, in this case, this is a kernel, like the one we're saying is 1 1 1 0 0. The kernel can take many other formats. For example, I would say 1 1 1 1 1 1 or 0 1 0 1 negative 1 negative 1. So, or I think there. So this one would be like another format. So imagine if we're working with this kind of value and you're having a like an image. Let's say it's this image is something like this. And let's say you have dark skin and we have like a white background, or maybe I should put like a panda bear here. So for example, if we're looking at something here. So maybe for those pixels, just in the extreme version, we're going to have like 255, 255, 255, like something like this, 255, like 100, 100. Use this kernel. Use this like 0 1, negative 0, negative 1. Imagine in this case, if we're going to have like a pet like this, like it's very high number on this end and a relatively low number on this end, when adding together these two, it's actually multiplication. Multiplication together these two will have like a very high value comparing if we're having a patch from here. Maybe let's say a patch from here. So this one will be like 255, 255. So it's like all 255, 255. So it's all the same. So if this one goes through the kernel, and it will have like a high value. But if this one goes through the kernel, because like this area where like there are like positives and plus the negatives, it will balance out. So this one goes through the kernel and will have a low value. Like 255. And also a patch from here where let's say it's like all 100. Let's see. it will also have a low value. So what are the difference between these three patches? If we're using a kernel like this, it will be very effective in detecting edge in this direction. So if there is an edge, like a boundary edge in this direction, it will generate a high value. If it is in a general surface, it has like less of the differentiation between the pixels, it will generate a low value. So this is why this kind of kernel or this kind of convolutional layers works very well with image, because it's very good with like detecting features. For example, like edge going like this. And if we want something to detect like edge going this, we probably would have a kernel that, of course, it's more complicated than this. I'm just putting it into something that people can understand. So we probably have like a kernel like this to detect this kind of edge, like going that direction. So basically, you can train different kernels to detect like edge conditions going in different directions. And those are very effective as to extract like the first layer of information. And it's also, if you look at it in a more abstract manners, this kind of kernel is very efficient in extracting the information based on the neighborhood conditions, like what is this the relationship with this pixel of this pixel in relation to its adjacent immediate adjacent neighbors. Oh yeah, quickly share our this screen here. So this is an intuitive way of understanding why convolutional neural network works very well with image processing. Let me stop this one. And also there is probably people has always asked the question of what the neural net is going to see. So this is like what it's actually going to see if we just take out the facial recognition, for example. So not all neural network can be visualized like this if we were just working with raw data. But if we're working with image, it's possible to extract the features or the like output neurons from each layer to see what actually the neural networks would see. So this is how things progress. So for the first layers, it's obviously the convolutional layers, and you start to have like edges like going on different directions. On the second layer, it start to combine edges into sort of like smaller regional features like eyes or nose or mouth, or like a contour of eye, contour of eyebrow, or contour of like chin, and etc. And on the upper layers, it start to combine them into like different faces, like fat, thin, different race or different directions, smile, anger. They start to connect them to even higher level features. So this is how like in general neural network works. It works from like lower level, very abstract features to more like higher level, more complicated features, and these things sort of builds on top of each other. And one problem, and if we're looking at this one, because I remember it's Boshen, you were asking about transfer, not style transfer, like transfer learning. So this is something we can use. This feature can be used for transfer learning. For example, for both dog and the cats, you will have the bottom, the lower layers recognizing like contours, boundaries, and etc. You will have the second layers to recognize like eyes, eyebrows, patterns, and ears, all those like smaller features of both and cats, dogs. And it's only up till the top layers, like the cat, the ears and eyes start to come together to driven a decision whether it's a dog or a cat. So the only on the upper layers, they can make a decision on like combination of the features to make a decision on whether it's a dog or a cat. And if this is this is the case of ideally there should be like another layer on top. So there should be another like a binary classification layer to see like to come up with a dog. Or so if this one is to classify a dog, I know it's a human, it's just imagining those are like dog faces. Or we'll say if we want to classify it's like a male or like junior high young adults or like elder. So let's just say it's classification of whether it's a dog or a cat. So all those features, like all those layers are the same. So it's only these last layers, like classification layers, that is going to make the decision based on all the previous features. So imagine we already have a neural net that can recognize all those features. And if we want to transfer this one from recognizing a dog to a cat, it's likely that we only need to retrain this layer. Sorry, it's going crazy. I'm trying to get something here. Yep. So instead of like a training like every layer on the like from bottom up, it's possible that we only retrain this layer, so this classification final layer. So this is how transform learning works. So like if you're having a case with very similar like feature points underneath, and it's only the decision is different. So it's possible that we use a pre-existing neural network and just train the top decision making like or the higher feature layers to transfer this neural network into another neural network of like a different purpose. But ideally, you should have like very similar bottom features. For example, you are never able to transfer this neural network into something that would predict like a housing price. That would never happen. But like transfer from dog to cats is possible. Another thing like in this process, so normally there, because before we were talking about GAN GAN network as a style transfer. So there are also, let's say, other ways to do like a style transfer is that if you look at the lower features, at one point you can understand them as like styles. And it's a style transfer is that if this is not a classification of to generate dog or cats, it's just some process to generate the face. For example, if we're giving them like I don't know, like a description or a drawing of the face, we're trying to generate the face of like a real human being, and you want them to generate like another like a different style, then maybe we can retrain like the bottom layer to, let's say, capture, instead of having like features from a real person, then we can change the features to have like more abstract, like Van Gogh features, or from like statues instead of real person, and just retrain part of the layers to achieve the same function, but with different style. So it's like another way to do style transfer, but it doesn't have like very good result as GNN network. So nowadays people doesn't use it that much, but it's a lot more like explainable than the GNN network. But that's like another way to transfer styles, that you can consider like this kind of lower level features as like styles. I think those are like the very interesting points and elements about convolution networks, and as well as for the, let's say, the image processing aspects. And another very interesting layer, so there are only not only two, there are like a lot more more different layers for a convolution network, but the two main layers or two signature layers are the previous convolution layers and the max pooling layers. I'm misspelling something, so it's max pooling layers, or what we call pooling layers. So this one is interesting. So this one works to reduce dimensions. And without, let's say, to reduce dimensions, but maintain the features. So and the benefit of these layers is that it's not trainable. So it will not impact your training speed. It will only impact your, let's say, data structures and complexity of your data. So a lot of people use this max pooling to reduce dimension. For example, in this case, basically what max pool is that if you're having a max pool of 2 by 2 and the filters, so it will just looks at this region. It works very simple. So all the neural network, like each segment works really simple. So basically, like by 2 by 2, it will look at this region and see what is the biggest number in this region, and in this case it's 4. And then we just only keep the 4 and disregard all the others. And then like in this region, so stride is like how much it move forward. So it moves 2 steps forward, stride is 2, it start to look at this region. So what is the biggest number in this region? It's 6. So we only keep 6. So you see, in this way, we have reduced image size of 4 by 4 to 2 by 2. So this is just a layer that we can use to reduce image dimensions. And of course, in this case, they can also have like a larger filter. So this filter is like 3 by 3. And in here, what's the largest number in this 3 by 3 area? It's 5. So it's 5 here, 5 here. And like a stride is 1, it means like each time it's only taking 1 step forward, and the step forward is here. So then this is the next step. And what is the largest number in this area? I think it's also 5. So this is also the largest number. So it's kept here. So, and what is the largest number in this area? I think it's 6. Yeah, 6 is here. So it's kept here. And the same goes on. So here is also 6. So this is like the max pooling. It works. Basically, it keeps the most significant numbers or in the giving areas. So, and it's able to reduce dimensions. You don't really need to understand why it works, but it's just like one common thing layers when we're working convolutionary neural network. Last thing we're going to talk about is regulation. So regulation is basically, remember, we're talking about, so this is not only explicit to convolution network. This one works with every type of network for every layer. So a lot of the layers will have regulation parameters. And if you're opening the keras and checking, have seen this regulation parameters, it means like how much of deviation or like this influctuation are we allowing this your, let's say, your layers to be. So basically, remember, we're mentioning the neural net is capable of mimicking any type of functions. And of course, for example, if it's data distribution like this, we all want them to capture something like this to generate a. So this one would definitely be overfitting. So it's just start like what we said, we develop something to capture the nuance and the smaller, like minor features while ignoring the big trend. So this is like overfitting. Oops, fitting, sorry. I'm writing with my mouse. So this is called overfitting, means we have developed a neural net, or this layers just captures too much the nuance of the details, and it's sort of, even though this one will have like a 0 loss on the training set, it will have a very high loss in the testing set. While like in this case, let's see if the testing set or validation set is something like this. this one will have a higher loss on the training set while having a smaller loss on the validation set. So this could also be a problem, because I think yesterday some people has mentioned that why are there like we're seeing something like this. So this is our training, and probably like sorry, I think the color is wrong, but it's probably this is our validation. So why sometimes the validation is lower than the testing, than the training. So this one could be like one of the reasons is that there are some hidden parameters, by default parameters, that are regulation in the layers. So if we're having regulation parameters in the layers, it's likely that we train it to capture this kind of overall trend. In the end, it has like more deviations, more errors on the testing, while like lower errors on the validation set. So it's a combination of the distribution of the data and the combination of the like regulation. So yeah. So that's like a very quick introduction on the CNN. Let's stop share. So I don't think we have enough time to load the new data sets and deal with like image processing of the timber and etc. But I think we can still test a little bit of the CNN with our current data set. It's 10 more minutes. So remember, normally we have like a CNC pad, something like this one. So this is like a 2D convolutionary network, but we can also have 1D. So 1D is just basically 3 numbers that works the same. And then you can define it's like 3 by 1 or 3 by 5. So normally you work with odd numbers. So it's either like 3 by 1 or 5 by 1. And for the 2D, it's normally it's either 3 by 3 or 5 by 5. Sometimes people use 7 by 7, but it's really weird. But normally it's just 3 by 3 or 5 by 5. So we can also use like a 1D convolution network to test our models. Just try to think about intuition of how this 1D convolution layer would work on our data sets. Just some intuition. So we're sort of expecting for the convolution layer to work better than the neural network layers, because if we're just looking at them, like we said in the sequence model, so this one will related to the properties of all the points before them. But we can also say like the property of this point will like closely related to its like adjacent neighbors. So that hypothetically, with some intuitive understanding of how the layer works and what's the reason behind it, we can sort of expecting that maybe convolutional layers can work better than neural network layers, but we don't know if it's going to work better than LSTM. So we don't know if this one is going to be better, but we assume this one will be better than, or we're just by some like intuition, we're thinking maybe this one will be better than the neural nets. So I would encourage everyone just to try this one with our current data sets and have a comparison between these 3 during like the break we're going to have between this session and the night session. So if you guys have like some time, just trying to run like different structures for the convolution layer, to run the CNN and RNN. So this is RNN and neural nets to see what are the difference. And I would recommend to control the variables. So maybe you could only have like the first layer that is swapping between neural net and the RNN or CNN. and have like the similar dense layer. So maybe this one, it can be other numbers. I'm just putting out an example. For example, this layer is like dense 64 and another dense 128. So keep the other layer simple, but just swap like, let's say 1 layers and see how the different network will perform. Yeah. Oh, and also the code. Sorry, I'm forgetting this one. So changing it to CNN is very simple compared to the like swapping the neural net to the like RNN. So the neural net to LSTM, because basically CNN start with a very similar data structure as RNN. So I'm going to quickly share this one. So basically, I don't think we need to max pooling. I think there's some problem with my computer. Whenever I put down this max pooling, this one start to like I'm going to have a dead kernel for some reasons. I think it's maybe some problem with my kernel, but anyway, so one simplest thing is just to swap your LSTM layers with this one, convolution 1D. I'm going to put it in the chat. And remember, we need to import this one. So we need to import something from here. Just on the import from Keras layers, we need to add the COVID, not COVID, sorry, convolution. It looks very like COVID, sorry. Like this COVID layer here. So basically, it's just adding one line to your model. Just replace the LSTM with this convolutional 1D layer and add this COVID from like Keras layer import, and you should be ready. Yep. And also you can change a few parameters like we have mentioned. It's that is the size of the kernel. So right now I'm using where is it? Data analysis with my model structure. So currently I'm having like a kernel of 3. You can have a kernel of 5 if you want to compare. And currently the output is like 33 neurons and 32 neurons. You can have more, but I think like some of it's just the 2 significant parameters you can play with, and you can always change like ReLU to something ALU or leaky ReLU or something. But ReLU is just more popular. I think we can just keep this one for now.
Can you copy all that text in the?
This one is already in the chat.
No, but everything maybe.
Okay.
Yeah. Thank you.
Oops. I have also hatched out some other line of code. You guys can have your own combination of things. Like cook your own gradient of medicine and see how it works. And I can have a put it on import. Just put this one up front. Sorry, I'm having a dead kernel. So anyone has some ideas or comments about the convolution neural network and all those style transfer, image transfer, or the neural net transfer? Good. So I would recommend that just everyone to play around with this like 3 most basic structure of neural nets and get some sense of their performance and what their like strength is during the next few hours. And for the tonight sessions, we'll go back to look at like the structure a little bit based on your experiment and to analysis why something works and why something doesn't. And please prepare your PDF, like at least like the best performance models from all 3 and 1 or 2 of your worst performance models. And please send it to our TA Zhu Guanqi because we need to prepare some like 2-minute videos to show the outcome of the workshop for Cadria. So. And also, if we have some time tonight, I could also introduce of some of the current progress in machine learning architecture, and we can have some brainstorm discussion on what to go from there. Great. So see you tonight. And if there are, I know we don't have like tutorial in between, so if there are any questions, feel free to just post them in the group chat. Okay, so I think the problem with the Timber project is that it was just presented in Digital Future conference like a month ago. I don't think they're having the paper published yet. But I can, I'm trying to look through it. Yeah, but I can send you guys like a PDF version of the paper, but just try not to distribute it around. Yeah. Great. See you, everyone. See you tonight.
See you.
Yeah.